Okay, hello, it's me again, Gaspar. So I'm going to talk about weird things. So I hope you don't kill me during the talk or something. Going to show some code, VHDL and Python. So let's go. First question is, what is object-oriented VHDL? It's probably the first time you hear this, because I am probably the one who is thinking about this. And that started with this guy and this paper. I hope you know this. It was 20 years ago by Jiri Gaisler. And what he did was he showed that this event-driven approach is not really a good way to do things. It's much better to have two processes in your design. One process is the combinatory process, where you will basically define all of your code or all of your combinatory logic, so all of the logic that you're actually doing. And second one is the sequential one, which contains all of your registers. So, but let's think about what does it mean to be object-oriented. For me, it means that you break your stuff down into two things. You have data, and you have some kind of functions that perform operations on this data. And in this way, you can create multiple instances. And I think that's like exactly what this paper was talking about, by having object-oriented hardware, actually. So next question you have is like, why am I doing this? It's a little bit different. For example, my HDL is like event-based, so I think it's not good today. MyGen is really interesting. If you know MyGen, then you actually know that it's based on exactly the same principle, right? Breaking your stuff into two things. You have combinatory logic and sequential logic, which is basically object orientation. But MyGen is like a generator. My program is not the generator. There are some upsides, there are some downsides. So let's give it, and I am focusing on DSP logic. None of these are not doing this. At least I know that they don't have like a fixed point class, for example. So that's my focus on DSP logic, but it could be useful in other places also. So I want to give some practical example. Don't be afraid of this. What we are doing is we are connecting two moving averager blocks. We are connecting them together. We are actually not going into this. We are using them as a black boxes. So two blocks, input goes from 1 to second to output, and the output we have to delay compensate. So that's like a common hardware thing. Okay. So here's the code, how to do it in Pyha. Which is my stuff. And now let's focus on this constructor part. And as I talked about the object orientation, that in hardware, if you have a data model, it has to be registers, right? Because you have data, it is memory, it has to be a register. So what we are doing here, actually, we are defining all the registers in the design. So, for example, we have a list of two moving averager objects that are defined exactly the same way. So it's like easy way to reuse your blocks. And let's now take a look at the main function. And this is the function that implements your logic, what you want to do with the data, basically. So I think the simplest way to understand this is to think about that this is what executes on a clock cycle, right? So each clock cycle, this code is executed, and how we are connecting these moving averager blocks is just by calling them out. We call out the first one, we get the output, right? Then the output goes to the input of the next one, and we have the final output. So it's like a pretty easy way, looks like software. You don't have to write some strange things that look weird. Now, how does this thing convert into VHDL, and how is VHDL in this thing? Let's focus on the data model again. So let's, for example, keep in mind that we have a list of two moving averagers. Let's see how it converts. It converts like this. It's pretty strange, I guess, but we are keeping the documentation. I'm keeping all the names. So I'm converting the data structure directly into VHDL structure. So this is the collection of all the registers in the design. Okay. Let's look at the main function. How is this converted into VHDL? Basically, the same way. Let's keep track that we are calling these two functions here. We are checking if the output is valid. Let's see how it looks in VHDL. It looks like this. Same thing. We're keeping documentation. We keep all the names. Now, the function calling thing is a little bit weird because VHDL started like limiting things, but I wanted to have the Python power to return multiple values and all that kind of stuff. So this is where I have to do some transforms on the code. But in the end, it's the same thing, right? We call two moving averagers, get the output, check if it's valid. If it's not, don't do anything. So I hope you get the point that Pyha is such kind of project that converts into VHDL directly, so line by line. And now you are thinking, how is this synthesizable, or is it even synthesizable, right? It is basically the same thing that was released 20 years ago by Jiri Gaisler. It has been probably synthesizable for a very long time. I personally have tested it mostly on Quartus system. It works really well. It scales really well. You can build big blocks. You can make a lot of components. It works. I have also tested this on Vivado. That was at the start of this year. It also worked. I had to do some hacks because I'm not officially supporting Vivado, but the style works. What else? So, only thing I have been having a little bit trouble is the blockgram. Like defining blockgram cannot work. So I'm also doing some hacks. I'm pulling them out of your data model. I'm putting them right into the top clock cycle so that the tools can actually find that you have a blockgram in your design. So in the end it works, but it can be a little bit sketchy. I want to show how I'm actually working with this system. So I have like, where is my mouse? Demo. So look, I am doing DSP design, right? So I have to have the model. So what I have done, I have made the model like a first-class citizen of the object. So it has the same interface as the main code, and it's just a floating point model that you can execute. And one reason for this is I have my own cocotb basically, That's how I test my stuff. I just have I'm just using the default tools in Python. I have a simulate function. It takes an input, gets me a list of output from the model. I can run multiple simulations. For example, the model simulation just runs the model, right? The hardware simulation runs the hardware code. And I have two more simulations. I have RTL simulation that converts to VHDL that then runs with actually cocotb and GHDL. And I also have a netlist simulation that runs the whole process through the Quartus system. And so you can simulate the netlist. So again, you can be sure that your stuff is actually synthesizable. So another thing I want to demonstrate is that I have a debuggable simulator, which is, I think, really useful. People usually talk about Python, you know, they like it, but there is like no type system. They don't understand how the hardware works, what are the hardware types, right? So you don't have to have a bug to use a debugger. I use debugger all the time to understand the designs. So, for example, we are the debugger now. What's the input? You can see it's data. It's data valid. It has data, some fixed point type. Valid is true. So now we could just go into these averager blocks. I don't want to do that. If you want, you can. But okay, actually, don't need that. You can see the output of this function calls. What happened is we got, again, data valid, but valid is false. What should we do with false data? Should not do anything, so we return false data. One other thing is, let's go here. Let's see until we get some valid data. Okay. So, like I told you, we have a cycle accurate simulator, right? So, should we update this value, right? The whole point of this system is that everything under the self, under the data model, must be a register. So this must be a delayed assignment, right? So 0 right now, and nope, it did not update. That's exactly what we want. It will update on the next clock cycle, and yes, I'm thinking about supporting something like that. Maybe it makes more sense to you, but I don't know. So that's about this demo. I have another one. So I have been using this system to actually do some real life cores, so things that actually work in real life. And I was wondering, how should I kind of distribute them? How should I document them? And I'm just trying out this approach of using Jupyter notebooks. If you know about them, they're pretty great. Anyhow, my point is to have like documentation for this, which is just taken from the doc strings, and overall have this giant playground where you can just come in. You can, load your own data file. You can run the same simulation, and you can see how this thing works, right? So, and also for debugging, I have a tracing feature that's like pretty cool, because you can see the output from each block, and the output is compared to the model on each block. So, like a really helpful tool for debugging. For example, this is the input stage. We have the model, and we have the hardware. They are mostly like equal, but hardware goes to 18 bits. So there is some small error in this, but that's nothing too bad. then, okay, what we were doing, we were passing the data through one moving averager, then to the second moving averager, and then subtracting it from the input data. So that is the first moving averager. And as you can see, this one already has some problems. Okay, no. Anyhow, that's the second moving averager. As you can see, there are some quantization effects. And lastly, the output, which we are basically compensating for the average value of the signal. Also in these notebooks, I have like the way to convert your design into VHDL. Thing about Pyha is that if you want to convert, you have to simulate first, because there is a need for these data types. And but it's not too hard. That's why I provide this block. You run this block, you get your output files in your temp file. And also I have integration to run synthesis and see what's up with your maximum clock rate. It's pretty good. It's all the stuff is going to the block RAM. That's what we want. Clock speed is pretty good for this device. So I have quite a lot of these kind of notebooks in my GitHub. So if you are interested, take a look. Okay, my system got messed up, but that was the end anyways. So what is the future, what I'm thinking about? I'm thinking about that this thing converts in a pretty straightforward way, like Python goes directly into VHDL. And what if we could instead convert into C and then push it through the high-level synthesis tools? So maybe you could choose if you want to implement your block in either RTL, then you convert to VHDL, or you want to do high-level synthesis, then you convert to C, and you run it to the high-level synthesis. So that's it. Thanks.
Questions?
You said we could find more in your GitHub. What's the address of your GitHub?
Yeah, it got messed up, sorry.
In the slides?
Yeah, it is on the slides, but
Yeah, then it'll be online.
yeah, I will talk to you later.
Apart from describing your RTL in Python, how much object orientation from Python itself can you use to model your designs, apart from just using Python to generate VHDL?
I didn't get exactly what you meant, sorry.
Well, if you model some abstract properties of units, of interfaces, how much of that can you represent in Python and still map to valid VHDL?
Well, you can have composite objects, so, but I am mostly working on DSP stuff, so I have a streaming interface, and that's mostly what I'm doing. I don't know if it answered your question.
That's good. Thank you. Sorry, any other question? Otherwise, let's thank the speaker again. Thank you very much.